Morning, everybody. So, the first thing that I would like to say that these equations I just put it here because it's you are very familiar with this equation, right? This is the fundamental equation that we have all come across from BSL from your transport class, and this is a partial differential equation, right? And so what we do is we take an equation like this, and then at the top of it we add the algebraic constraint, and that gives you the PDAE. So like when we look into the species conservation equations, let's now actually previously when you have done it in your transport class, the idea was that how you simplify based on certain assumptions so that you can analytically solve it. But now what we want to solve is that the full equation. Let's say I don't want to simplify anything, right, and still would like to solve it. So that's the idea that what we have right now. So let's look into each of these terms here. What we have here is this is the time derivative, right, which we are talking about. This is the convective transport that which we have for any of the systems. These are the components in the x, y, and the z direction. And then this will be a diffusive transport that might involve, so it may or may not be there. There may be additional terms there based on the kind of transport that you have, and then you could have a reaction term also. When you look into the energy conservation, the same thing, this is the part where we have got the time derivative. And then here what we have is the corresponding terms for the convective transport, and then we have got the conductive transport, and then we could have any other kind of heat that it is interacting with the environment, right? This could be some heat of reaction, this could be something that is coming through the boundary, there could be an electric heater there. Like this type of things becomes important if you are considering a say when I'm considering desorption and I want to provide a lot of heat. So how do I provide those heat? So these are the ways to incorporate those extra heating terms. Like if you have an electric heat that you put into the system, this is the term that comes into it. There are also some projects that we are working where microwave is used for heating, like rapidly heating. You use a microwave to rapidly heat up for desorption. That's also, these terms will actually capture those type of things. Also, one thing that we'll keep discussing more and more is that one issue with the solid sorbent is that they are stagnant, right? There is a bed and they cannot live anywhere. So that's a problem with the solid sorbents, that whatever temperature picks up, who takes away the heat? So only the flowing gas will take away some of the heat, but as we know that the specific heat of the gas is very small, so they cannot really take much heat. So it's only through the flow rate you will get some heat out. So quite often that's why you have an embedded heater or a cooler. So you put a heat exchanger locally through a cooling water will be wrapping around, and without that you may not have really achieved much adsorption at all. If your heat of adsorption is high, an embedded cooler may be needed, right? So those type of, when you consider those, this is the term that will capture it. So I just put it like a catch-all term, right? This can cover many things. With these equations, any question here? This is very generic, and but we will be taking these equations. Basically, this is where from the adsorption models are obtained. Everything is in Bird-Stuart-Lightfoot. Everything. It's only some modifications you do, but everything is, you can directly get it from Bird-Stuart-Lightfoot. All the fundamentals are there. Okay. Now we go. Okay.
About the convection and the conduction,
Right.
when the gas medium flow through the penetrated medium, mainly the heat is moved from the surface to the conduction.
Right.
But in convection, one more thing is the radiation.
Correct.
That is not applied here. is it necessary to include convection here? Only can you go with only convection?
Yeah, this is just the entire equation, but you have to really see what else is going on. So some cases you will see, like when we'll go into the specific equation, I know Dr. Palla is also going to go about those equations. I will also cover some of those equations. You will see that we do not use all the terms everywhere. Like for example, when we are considering within the pores, right, then we'll be mainly talking about these terms there. When we are considering the bulk flow, we'll be mainly considering these terms here. So we'll be keep doing it. Radiative heat transfer, because the temperature remains very low, it's generally very negligible. But if you are operating it at a high temperature because of some reason, then yes, you can consider that. Yeah. Okay. Very good. So I will go back to the same problem here, that what we had is that when we try to do a dynamic model for a PFR, and you see that here I did not consider this. So this is the same term, same equation that I took, but what I did was I neglected all these components over and here, and just I retained only this term and particularly this term. Those are the only two terms that which we kept. This is for simplicity. You can consider more terms there, but this is a simple model that which you have read in Levenspiel's books or Fogler's book, and this is a simple equation that which we considered that. Why I'm actually showing it here is that because in the afternoon, that demo that I will do, I will show you some of these things. Other things will take you a lot of time. So it's a simple version that is amenable to in this class actually, and see how we can actually solve it. So, and then other equations that which we have for a PFR model. So the point here is, without this, it is a steady state model, and then when we are doing it, this will be a dynamic model, right? And what in this class, what we really need to be very much used to is the concept of dynamics and change in both space and time. Generally what we do is that either we consider time derivative, we neglect spatial derivative, as I said yesterday, those are lumped model, or we ignore the time derivative, we only consider the space, and those are steady state model. But these systems, the adsorption systems, has got both change with time and space. So we cannot ignore any of these. So this is the type of model that we need to get used to it and understand. So you'll see, I'll always be talking about the dynamics and all of those stuff. So please stop me if there is any difficulty in understanding. But before I go forward, if I say, okay, this is a steady state model versus this is a dynamic model. So let's have a quick discussion. If I'm considering a PFR, right, we have all started, like starting from our undergraduate classes, we do plug flow reactor, and we do not solve them dynamically in the undergraduate, like it's mainly solved steady state. So when we solve for steady state and when we solve for dynamic model, is it arbitrary that I should solve for dynamics at some point of time and steady state at some point of time? When should I consider dynamics of a plug flow reactor? Anybody? Startup, right, excellent. Or just startup condition, shutdown condition, or when actually there are changes in the boundary taking place, right? Practically, if you go to an industry, like in our classroom type of an example, we consider the composition is constant and blah, blah, but in reality, they are not. There is never like a constant composition feed is coming in. Think about a petrochemical refinery. Think about coal. Think about a natural gas. This is coming from under the ground. The composition is actually always keeps changing. So it's never that steady state. We just approximate it as a steady state. We say, yeah, it's reasonably close to steady state. But adsorption is something will never have a steady state. So this assumption is not possible for an adsorption, and as we keep discussing this, you will see that why it is not. There will be more discussion tomorrow. Now question is that if I give you a problem like this, how do you solve it, right? Even like a simple problem like this, there are two derivatives. One is with respect to space, one is respect to time. So how do I solve this problem? So in the numerical world, the most common approach is called the method of lines. So in method of lines, what we do is we discretize in all but one direction. So we never discretize the time domain, but we discretize the spatial domain. So remember yesterday's class, I was talking about finite difference schemes, right? I say backward and the forward and the central difference. So what you really do, you take this one and you apply one of the forward or backward or the central difference schemes. Once it is done, this becomes algebraic equation. But what happens is we are not losing the concept of the space. So essentially what we are doing is if I have a plug flow reactor like this, when I am discretizing it, I am considering each of these locations. So I need to solve this problem at each of the locations. So I need to solve dci dt here, dci dt here, dci dt here, dci dt here. All of these locations I need to solve this same problem because I discretized it. The discretized is the space, but this time derivative remains. So I need to solve these equations at each of these places. So if I am discretized more, simply speaking, I am actually increasing the number of the time derivative that we are considering that I need to solve. So if I do discretize it into 1000 pieces, so I need to solve 1000 of these equations, and that makes it complicated. So more discretizations makes it more accurate and more computationally expensive. But this is the technique by which we go. This is known as the method of lines. So what it does is that we take the PDAE, so it will convert these to a DAE, differential algebraic equation, which we discussed yesterday how to do it. However, what I discussed yesterday was that we talked about the finite difference schemes, but we applied that to spatial derivative. Now we have a DAE, but instead of the spatial derivative, we have the time derivative. So this is different. So remember yesterday when I was discussing about DAE, I was just simply talking about this guy over here, right? This was spatial derivative, and we applied the forward or the backward or the central difference here. But now we already discretized, we are left with this guy. This is time. This is different. So time cannot be treated the same as the space. They are equivalent, but I said time cannot be treated more similar to space. In terms of, you can apply similar scheme and the thought is the same, but it cannot be treated the same way. Anybody has a guess why we cannot treat the time as the same as the space?
So the time-dependent problem has only one boundary condition, the initial condition.
Right.
In space you can have two boundaries.
Exactly, that is one of the things, and then the spaces can be coupled, but time at future time cannot impact the current time. Like I cannot say what will happen 2 hours from now is going to affect at t equal to 0. No, it cannot. But in the space, it can be completely coupled, and then what is happening downstream can affect upstream, because you can clog something and the flow will go down, or you might have a pressure drop downstream and you cannot do this. So this is one of the very key differences between space and the time. So we can take the liberty, we say, yeah, for the time I'm actually marching forward, but the time has a problem. In the space, we are bounded. We are basically saying, this is my reactor size, or this is my distillation column size. But space, with time, no. I can solve for 1 day, 2 days, 10 days, 10 years, 30 years, 1 million years, like if I'm doing for CO2 sequestration problem, people are simulating for million years, right? That basically saying, well, I'm storing CO2 somewhere, maybe can it happen that one day that CO2 might come out and kill everybody around that neighborhood, right? So those are a million years simulation that people are trying to solve. So it depends what you are trying to solve here. So that's one of the differences. So the thought is the same, but there are some fundamental differences. So one of the common technique that I will be discussing here, and it's also implemented in, I think MATLAB does not have an implementation of a lot of these approaches, only some variants of it. ACM has, the Aspen Custom Modeler has the implementations of this. In Python, there are actually some implementations of these ones. So this is a very powerful technique, and I'm sure as part of your numerical methods class, some of you have taken and understood some of this. So I'll recap some, but I will talk about more practicality of applying these approaches also. So what we are trying to do here is, once I discretize, this is the problem that I'm trying to solve, right? We have got many of these equations. So this is the general linear multi-step method. So massive amount of variations of these yield all the techniques that you have learned in your class. As you are changing these things, like how many terms you keep and how you actually compute this, you will get all kind of equations. You can get explicit Euler, I'll show you implicit Euler, you can see all the techniques from Adam Basford type of techniques, and all of these other approaches that you will find with first order, second order, third order, fourth order, all will come from these general equations, okay? So here, this is how you generally solve these problems, and then based on these, you cannot retain, like question is how many k's you keep, how many m you keep, that is where the order and the error of the terms keeps changing, okay? So here alpha naught equal to 1, alpha 0 equal to 1, that basically means that I am predicting for yn plus 1, starting considering yn and other terms, right? Now note that if I consider that beta naught equal to naught 0, that basically means that I am keeping the 0 term over here. So we will have f of x n plus 1 y n plus 1. That basically meaning that I am considering y n plus 1 depends on f of x n plus 1 and y n plus 1, right? So ensure that that is getting clear as it is written. So if you substitute, if this is not 0, that basically meaning is, and I already put y alpha 0 equal to 1. So if I'm doing it, so this is 1, so this will be y n plus 1. So I am saying y n plus 1 is equal to whatever, and then something, and then I will have f of x n plus 1 y n plus 1. Sorry, it got probably so close. Let me write it here. Okay, so y n plus 1 is equal to bunch of terms plus bunch of terms, and f of x n plus 1 y n plus 1. You see, everybody? So that basically saying is that this depends on this. So when it depends on the current step itself, it becomes an implicit method. So there are all methods that which we are talking about becomes an implicit method. If it is not, we call it an explicit method. That's why we do the implicit Euler, explicit Euler, like we have always done that, right? Can anybody recall that what are the mainly the issues that I'm sure as part of your graduate class we all discussed that what are the issues with the explicit approach, because implicit makes it very difficult, right? Because when I'm trying to solve this but I'm saying this depends on this one, so I have to solve this together. In fact, if I could actually make our life a little easy and I simply say xn and yn, this becomes an, in this case it will become an explicit, right? And that makes it easy, and the first order explicit method is an Euler's method, explicit Euler. So what was the issue with this explicit method? Sorry?
The error keeps increasing.
Okay, it keeps increasing, and so for decreasing that the time step has to be very, very small, very small. So you have to take many steps there, right? So as we all recall that. So now this approach is called multi-step if this is greater than equal to 2, like if you substitute it. So say if I am considering it j equal to 2, so then I will get n minus 1. So this will becomes function of terms like we'll have f of x n minus 1 y minus 1 and similar terms, right? So as we keep increasing, when we have these previous terms being considered there, then we call it a multi-step approach. So I'm saying I want to find out the value at yn plus 1. It not only depends on n or n plus 1, but it also depends on n minus 1, or maybe even going forward I can consider of x n minus 2, y minus 2, and so on and so forth. When I consider these are called the multi-step approaches. Okay. If the order of the method is p, and we will be talking about that, like this is the kth order that which we consider here, then the local truncation error. So this is always we will be defining this local truncation error. This should be of order hp plus 1. That basically means is if I am actually considering a first order method, so this will be order 2 and so on and so forth, and I will show you in a moment. Then these, so what are unknowns here? These alpha I and beta j. This is the coefficient equation that you need to solve, and q is equal to 0 to k plus m, and when as you keep substituting it, you will get actually bunch of equations together. Is it not working?
It is work, but some
Okay.
disturbances.
Ah, right. Okay. Yep. Thank you. So this is the, so basically what you do is that you take this equation, set alpha not equal to 1 and solve these equations, and then you are good to go with many different type of integrator. You can discover many different type of integrators. In fact, actually when this equation showed up, people realized that actually lot of the standard integration approaches came from this general equation. So you can apply these equations to lot of integration techniques, right? So if I take these two equations, and then this is a very busy slide, but I will keep going back and forth. If I would say k equal to a1 and m equal to 0, so that means this equation k equal to 1 and m equal to 0, that gives me that implicit Euler method. And you can substitute all kind of numbers there before, and you will see all kind of Adams-Moulton, Adams-Besford, all equations, everything will actually show up there. One of the powerful method I would like to note here is that which I will suggest you use in Aspen Custom Modeler. I think this is not yet implemented in the MATLAB ODE suite, but it's there in Aspen is called the Geertz method. This is kth order backward differentiation formula, Geertz method. So what we really do there is beta naught equal to not 0, all other betas are 0. So that means here I am only keeping m equal to 0. So we just keep m equal to 0, and then and then I can actually, if I do that, this is the equation that I get. So if you notice here, this is the overall equation that I get if I set m equal to 0, because there will just be only one term, but this will all remain there. So from here, as I keep changing the value of k, I will get different order. So these are the errors that I will get, and how we are getting these coefficients here. These coefficients are obtained by solving these equations. I am just not doing it, showing it here. You can find it in numerical methods book there, or you can even solve it yourself, like substituting these equations and solving for those coefficients. But this gives you a varieties of method. So when you go to Aspen Custom Modeler, it will give you an option, say Geertz method, and it will say maximum order, and you will say yes, 6 or 5 or whatever. It's up to you. Then what it does is that if it will start with that maximum order that gives you the highest accuracy. If it cannot solve it, it will keep cutting. So it will say, oh, I start with the 5th order and I could not converge. Then it will go to the 4th order. It could not converge, it go to the 3rd order. It could not converge, it go to the 2nd order. It keep going. This gives you a lot of flexibility in terms of the solving the system of equation. But when you click those, and I will show you today where it is, when you click those, you know this is actually what is happening. So higher order means the lesser error, but it can be computationally more difficult because you are seeing that what terms it is actually keeping, and then it becomes actually more difficult for it to converge. And it is okay to actually go for a higher error. So remember, like generally as a researchers, we always want the highest accuracy. But one thing you have to always keep in mind is the stiffness of systems. So when a variable changes like this, it goes like this. This is extremely steep. It's almost like a vertical line. Most solvers have trouble in getting into that. But if you really want to get the results, if it is actually instead taking a step something like this actually ease out it quite a bit. Just a little shifting, instead of saying it's like a vertical line, you just actually have a little bit of an error somewhere around this zone here, and you will be fine. So remember that if you ever seen an industrial simulator, I'm not sure anybody has seen an industrial simulator, like many refineries I know they have it, they train their operator before they actually operate a plant, they take you to a simulator and train you there. Those simulators actually do these things routinely. They live with an error. Basically they say, yes, it's fine, I live with an error, but I'll catch up in the future. So this is living with a little bit of an error and inaccuracy, and then you go with it. You can actually say, no, I don't want to live with an inaccuracy, then it can have a convergence failure. But this will, at least you will get some convergence, and you can then compare how the results look like. But can anybody anticipate what is one of the issues with any of these approaches? What gets involved? Like, for example, you might argue that yes, this is the same function that I'm actually solving. So what is the issue when I'm actually increasing the order? Yeah, so you are increasing these guys, right? So you have all of these terms in your memory. You have to retain first thing is one is the memory management. So the moment you do this, you have to keep all the previous terms in the memory there and keep it. So that is one thing. Second is because this becomes constrained with respect to the previous values of that variable. So these equations in essence, it's not only the memory management, it is a bit difficult thing to keep holding on to all the variables here if you click one of these, but it is also because of it becomes actually it constrains the overall system of equations. So with this additional term, so it makes it can make it more difficult for you to converge all of those. Anybody has any question so far?
Sir, higher order will also increase problems with the boundaries.
Yes, it will. So, and especially when you, with respect, there are two things which we'll be discussing in a moment there. One is with respect to t equal to 0, and one is with respect to the spatial boundary. The question is there a stiffness around the boundaries? So how you actually handle the stiffness where the boundary? It could be a time boundary, like at the initial value problem, or it could be a spatial boundary. And Aspen gives you all the flexibility to saying, yes, like as I was showing you here, you might actually relax it. You can actually, in the spatial boundary also, you can relax it. You can actually have to put more discretization in the spatial boundary. So there are a lot of options that is there. So quite often around the space or the time, there may be issues in terms of convergence. Yes, absolutely, you're right. Any other comment here? Fourth order Runge-Kutta method. This is the standard approach that which we have all done this, and then this could be also different orders are possible. Fourth order is very common, and you can adjust all of these things, and this is we have always done this, right, as part of our undergraduate and graduate classes. One thing that I wanted to say, this is generally many times we do not teach in our classes, is that something called an adaptive step size. This is important for the solving steep problems. One of the confusion that comes there is, what should be your step size? Should it be 1 minute, 2 minutes, 1 second, 0.1 second? How do I know as an user what should be my step size? Because the solution that you are trying to get depends on what is your step size. So let's see that we understand what is the issue with respect to the step size. Why does it matter to have the step size? So think of your y with respect to t changing like this. Say if I have a large step size like this, say this is my step size. How much this variable is changing? This is jumping from here to here. This is a very tough problem for any of the solver to solve. Like, remember, and I will be repeating that thing again, behind the scene it will be a nonlinear equation solver and a linear equation solver that will finally solve everything, right? But is this value a good initial guess for this one? No, it's really far away from this. So during this time I may be like to solve here. So I have to cut step like this. Very small steps I have to take, like baby steps here. But once I'm here, I may be able to take larger step. I may go like here. Then when I'm here, there is really not much changing here. So I can take larger step, right? But the point you have to think about it is that because I draw this profile here, it is easy for you to visualize it, but this is a chicken and egg problem, right? I do not even know that the system will behave like this. So how do I know that I need to cut step here, and here I can go for a larger step, right? That is why you need an algorithm that will tell you that now you can increase the step size, or nope, keep cutting step, keep cutting step. So that algorithm is basically the adaptive step size. I will say for an adsorption desorption type of an approach, you must always use an adaptive step size solver. If you use any other solver, it will not, most cases it will work because of the adsorption front and based on the specific adsorbent that you are actually considering. If you have, and we'll be talking more about this, I'm probably putting the cart in front of the horse here, like going ahead, but I think for our discussion some of these things will be important. One of the things, as you will see, that we will be looking forward is considering something called a breakthrough curve, right? We'll be discussing that quite often. These are known as the, okay, I should probably write more clearly. This is the breakthrough curve. This is C over C naught, and this is with time. So if I have an adsorbent which has got very less kinetic resistance, this guy will become like this, and this will become more elongated except if we have more and more resistance. So it will be like going like that, right? It will bring more and more elongation. So if I have something like this, it's actually very difficult without using an adaptive step size solver to really solve this problem. So how do you actually adapt the step size? So I need to know that here I do not need much step. At this point I will be taking a lot of steps, so I need to cut steps. Here I really do not need much of the steps. So one of these approaches that, let's say if I'm using an RK method, fourth order Runge-Kutta method, what you can do is that you can do fourth and the fifth order RK method to estimate the local truncation error. Remember my definition here? I define this is the local truncation error, yx at n plus 1 minus yn plus 1, right? So that is what I actually have a typo. I see this. So this is actually yn. So you read it as yn plus 1 minus yn. Sorry, this is a typo. I'll correct this. So once again, local truncation error is whatever is the value that I have at n plus 1 minus yn. So that's that local truncation error that I have. So what you really do there is that you apply a fourth order method and a fifth order method, and then you estimate that what is the error that I would have gotten as a result of this with this. If you are using some other method like Euler's method, then what you do is that if I am going for a single step versus I am taking two steps, what is the difference of the results? So that just to ensure we are on the same page, say this is the profile I am trying to capture. This is say y with respect to the t. Say this is the overall h that I took, like one single step I want here, go here, and I get some result, versus I take two steps, h over 2 and h over 2. So this is what is actually being shown in this profile here. So if I am taking two steps, say I am taking one step, two step, this is the result I will get. Instead, if I would have taken four step, this may be the actual result that I would have gotten. If I would have taken 6 steps, this will be here, and if I could take infinite steps, this will be the result here. So what you are saying here is, after certain number of steps, it does not matter. That's the idea that you have, like you take more steps, but beyond certain steps, the difference is not much. So that is what is happening, 2 steps to 4 steps for this particular graphical depiction of what's going on. There is a much difference in the results, but then after that it does not matter much here. So that gives you an estimate of the local truncation error. If that local truncation error is smaller than the tolerance, then you increase h. So what it basically says is that, okay, if I'm actually doing this, say I take h over 2 and I take a 1h, and the result I'm getting by this is here. So this is the difference, right? I'll show you clearly here. Say this is over h over 2, but when I go here, say this is the result I got. So this is really the difference or the error term. So this small difference is that error term that I'm getting here. This tells me if this error is below the tolerance, then I increase the step size. So if this h was, say, 1 minute, then I will say, okay, let's increase it. Let's make it 2 minutes or 3 minutes or 4 minutes. How much to increase? That's a different thing, and I'll talk about that also. But basically idea is that you need to increase it. If it is below that tolerance, then it basically means that you need to reduce your step size. So all these solvers, like these approaches, if you have used MATLAB before, these things are not available in MATLAB, but you will see in Aspen this option is there. It basically let you know a minimum step size and a maximum step size. This is what it means. So that basically meaning is that as a user you are saying, I cannot let you take more larger step size, but the minimum step size is basically saying you keep cutting as needed till the time that you will not exceed that lower limit, right? Then there are different methods exist on how to adapt based on the truncation error. As I said, I'm not actually going too much onto it, but one of the method is known as the Richardson extrapolation method with Burley-Stewart method here. This basically actually approximate using a local model. So it is basically fit a local model with respect to the number of steps versus the truncation error, and that local model is used to predict if I am actually increasing the step size or decreasing the step size, what is expected to happen with respect to my error term, and that's how it actually keeps adjusting it. So once again, the takeaway message from this slide is that for adsorption system simulation, especially when you have a steep breakthrough curve like that, adaptive solver is absolutely critical for you to have success. Even within the adaptive step size solver, there will be two things there. Just to ensure from this algorithm we understand it, one is the minimum step size, another is the maximum step size. What it basically means is that if the truncation error is higher, then I am saying decrease h. But I cannot just keep decreasing h infinitely. There is a place where I have to stop. That is, it will stop at the lower limit that you specified. So say I specify the lower limit to be 1 minute. So first I take a step of 5 minutes. It did not work. Keep cutting, and then it will not cut below 1 minute. So if it cannot solve at 1 minute, it will basically say, sorry, convergence failure. On the other hand, if you satisfy the local truncation error and you increase the step size, which you want to do here, right? Then what will happen is at some point it has to stop. So whatever upper limit you provided, like 5 minutes or 6 minutes or 10 minutes or whatever you provided, it will not let it go beyond that. So this is how this thing is done. I'll stop here for a moment and see anybody has any questions for me. This is an important two things which I discussed: multi-step and adaptive step size. So both concepts I want to ensure that is clear, because you will face convergence failure, have convergence failure. That's the reality. You should. I'll be very surprised if nobody has convergence failure. And that is where our knowledge comes in. And this is where our understanding is important. Mathematically, what is happening, what is blocking us, and how it is happening. So, any questions here, please?
How do
Yeah, whoever, it doesn't matter.
you decide the end of all time steps?
So I'll show you where the tolerances are there. So Aspen by default, I think it is 1e minus 7 is the tolerances that is actually specified for these ones. But as an user, you can actually cut those tolerances, and most cases, many cases, what we generally do is we do actually a sensitivity study. Many cases, what you will find is that it's probably one of these places there will be little differences. After that, it will make no differences. You can do a sensitivity study with respect to a tolerance. Many times with a very small tolerance, you take many more steps, but the results are very little different actually. Yeah, there is no sanctity about telling a tolerance how much it should be, but below 1e minus 3, like normalized values, would not recommended, but 1e minus 5 is actually very standard, but you can go definitely go higher. Yes. Okay. So the way you have to really see it, and I will talk more about it, is that how these tolerances are actually defined. And there are a bunch of tolerances in Aspen you will see. Many tolerances. So as you know, and for equation solvers, we have got many tolerances. One is the relative changes in the variables, like when I am taking a Newton step, I'm basically saying xk plus 1 minus xk over xk. That's the relative differences I'm saying there. The other thing is that about the equation tolerances. So the error, I'm getting the same thing, epsilon, which is the equation error, and then that is basically I'm saying those subsequent steps, and then I'm normalizing it. Question is that what does that tolerance really mean for you? I'll be talking more about this because the scaling is important, and you can sometimes we actually do not care about that. Like for example, if I'm writing an equation, just I'll give you a quick example, and then when I come to SEM, I'll give you an example more clearly here. For this particular example, I will go to this equation. This particular equation, I write it like this. Anybody tells me what is the unit of this would be? Any of these terms, like for dimensional consistency, our unit should be same, right? So say rho kg per meter cube, Cp kilojoule kg degrees centigrade, this is degrees centigrade, and this is second or minute or whatever, right? That is what we get it here. Degrees centigrade goes there. So kilojoule per meter cube second. This guy is kilowatt. This is kilowatt per meter cube, right? If I would have written these equations in terms, instead of writing these in terms of kilojoule, assume that I wrote it in terms of joule. This becomes watt. I could have also written in terms of megajoule, and this will become megawatt. So you see the same equation. When I'm trying to solve, I will get different error there. If I'm doing it if my actual error in the solution is simply say, just hypothetically, I assume that I'm solving this equation and that error is the equivalent of 1 watt per meter cube. And if I have a tolerance of 1e minus 3, this guy will not solve. If I'm doing it in terms of a kilowatt per meter cube, this will become 0.001. So this is about 1 e minus 3, so it will be fine. If I'm doing it in terms of the megawatt, so it will be 1 e minus 6 megawatt per meter cube. Yes, it will solve immediately. So you see the unit is very important. So this is something which we always overlook. So Aspen internally, they actually, like if you see Aspen Plus, they actually use gigajoule for many of those things, and it keep a very high tolerance there, because many times these terms are actually notoriously difficult to solve. The other thing everybody has to be very careful, and I'll discuss some of this later on, is the pressure unit. This is the one that kills everybody. Pascal is the SI unit we use. Pascal is a very small unit. Very small unit. Use bar or atmosphere or something that makes sense. Like 10 to the 5 Pascal that you have to go to a bar. Do we really care about 1 Pascal, right? But if the error is 1 Pascal, this guy will keep iterating. But do we really, and from an engineering application, it probably doesn't matter. So one thing which is important is actually your units, and I will be discussing today in the afternoon. I will always recommend to normalize the equations and variables so that the result that you get actually is meaningful. So if you keep everything between 0 to 1, there are techniques by which you can do it. So you will never write an equation like this. I would never write an equation like this, because this becomes actually, it all depends upon the units that I'm actually considering it here. So simply think about it. If I have an equation y minus x is equal to whatever, say 0. This is an equation I'm solving. The same equation I can write y minus x minus 1 equal to 0. They're mathematically equivalent, they're not numerically equivalent. I'm normalizing it. This is actually 1. So this, with respect to this, I assume that this case, this is 10,000, right? And this guy becomes 999. This error, this will give you 1. And this guy will, oh yeah, 1 e minus 3. You will keep iterating. It will never solve. But if I actually do this, I'm simply dividing 10,000 with 9999. One of you can actually find it out what this error will be. I think this will be like 0.0001 or something like that, which basically tells you that this is close enough. I can say this is perfect with me. I'll be discussing some of these, but remember, when you code, you never should code the equation, never. You have to think about the coding. Before you start coding anything, write equation, derive equation first, understand what it is. But then when you go to the coding, you have to think how to code it, make it well posed, and things like that. So, yeah. Any other question? That's what I actually be talking about. That will not only non-dimensionalize it, sometimes it actually becomes a bit difficult and you have to think through it. So when you non-dimensionalize it, even then the question is that are they scaled between 0 to 1? Because otherwise the tolerances are being applied across the board to everybody. So it may be only certain equation that is causing trouble, and those are not scaled. But all equations are important to you, the same importance, right? All equations we have same importance. So I will be, if I'm actually normalizing them, that basically means it's a fair game for all equations. It's not like that pressure drop unit, because I did it in Pascal, that's the equation that always keeps popping up because it cannot solve it. But I decided to do my energy in terms of gigawatt or megawatt, and I can easily solve it. That's not a fair comparison, right? So I'm solving one equation to very high accuracy, but other one I'm neglecting. So those are other tricks that which we need to think about. Okay, any other question here? Okay, very good. So this is the overall approach to solving the PDAs. Okay, I'll first describe this. I kind of described this yesterday and today, but I'll walk through it. So the first thing we do the numerical integration. So let's say I use Geertz method or RK method or one of those methods that I'm actually using it. After that, it goes to a nonlinear solver. So remember once again, this is the type of equation you are getting, or these are the type of the equation you are getting. So the moment you get this, it becomes an algebraic equation. That is why I was telling yesterday that even in the computer simulation, we are always doing a discrete time simulation, because this based on the step size, I'm calculating it, right? But these are converting these to an algebraic equation. So that means after the integrator is done, it creates a bunch of algebraic equation, throws it to the nonlinear solver. Yesterday I said that most variants of the nonlinear solvers are some flavor of Newton based method, right? And obviously there are many variants based on how you are calculating the derivatives, how you are approximating it, how you are calculating the step sizes and all of that. But first approach there, remember I said there in that there was the first step is that you have to solve for the step size was, so this was the equation that I wrote, f of xk pk is equal to minus f of xk, right? Remember that was the equation. So this is a matrix equation n by n. This is the guy that takes most of the time. So linear equation solver takes most of the time, depending on how gigantic your system is. So if you are saying I have got 10 million by 10 million, this is a 10 million by 10 million matrix. In previous generations, like most of these computers will actually run out of memory actually to do these things. So they do a lot of decompositions behind the scene and say, this is, can I handle this size? Can I make it chunks and all of those things? That's the power of the linear equation solver behind the scene, because it actually doing all of those things behind the scene to see, do I need to solve this 10,000 by 10,000, or can I separate it based on like 1,000 by 1,000, this 1,000, this 2,000 by 2,000, and then I combine those things. So that's what the linear equation solver does. So that is the guy, takes a lot of time. Once it is done, the first thing is that if the linear solver cannot converge, so remember I was telling yesterday that when the linear solver may not converge, like when say it is doing an LU factorization, or it is doing an LDU factorization, or it is doing another common method is the Cholesky factorization, QR factorization. So one of those methods from the linear algebra class you might remember, once we do that decompositions, it may immediately tell this is ill-posed. Like I said, the diagonal elements shows up as 0 in the LU, you are in trouble actually, okay? So once it finds that, it basically say, well, sorry, I could not converge it. So linear equation solver itself might say, I cannot converge. Then the first thing it says that is h, the time step, is still higher than the limit that you set. So say it was trying to take a step of 5 minutes, then it basically says, sorry, with the 5 minutes I could not solve. Let me try a lower value, but did you set the lower limit at 5 minutes itself? Then I have nowhere to go. If you set that lower limit to say 1 minute, then it basically say, okay, I tried for 5 minutes, I could not solve, it's okay, let me cut steps. So in Aspen, it generally cuts step by half. So if it is 5 minutes, it will go for 2.5 minutes. So then it will cut step, and then it will come back through this route again. If the linear equation solver goes through, then it will go to the backtracking line search or a similar method. There are some variants. I just kept it as a simple things. We need probably bunch of classes to go over these numerical methods things. So I just make it simple. Don't take it in the face value of it. It's actually more involved than as I mentioned over here. But think about a backtracking line search that we discussed yesterday. Remember in the backtracking line search, one of the things as I mentioned there is that it keeps cutting the alpha k lower and lower. If the alpha k value becomes lower than certain value, that means I'm not making any progress at all. Wherever I am, I'm exactly at that point. So in that case, it will come here and it will basically find out that if that alpha k is below some small value, that means I'm not making any progress. At that point, it will basically come back here and say, can I cut the step size? And if the answer is yes, you are still not reached the low point of step size, then you will cut step and go here. If it has converged, then it will adapt the step size. Now remember how to adapt the step size, I mentioned that adaptive step solver there. So it will then go to that algorithm and basically find out the local truncation error, and it basically say, should I increase it? I took a step of 1 minute, can I make it 3 minutes, or can I make it 4 minutes? So then we'll adapt the step size and go back, and this is the approach that actually it keeps going. Is it the, I'm not sure, we are probably done, it's 1, right? Yeah, that's why I saw the lunch. Maybe I'll take another 5 minutes, and then after the lunch I'll continue with this one and then go there. So this is the overall approach. Anybody has any questions about this thought? I decided to draw a simple cartoon here. Behind the scene, actually many steps are involved there, but this gives you an overall idea. Any question? Yes? So there is something which we can draw from the CFD literature, which always does these things very routinely. And one of the things is something called a grid sensitivity study. So if you say n equal to 20 and I got some solution, so I say y equal to t. So this would be one of the key performance measure. And for the adsorption, the key performance measure is the breakthrough curve. So say with this, I am getting this profile. Then what I do is n equal to 25. Maybe this becomes my new breakthrough curve. Then I say, oh yeah, I have a lot of error here. This is not acceptable to me. Then I go to n equal to 30. And this might be something very closer to here, and you are saying, okay, this looks closer to me, so let me stick to n equal to 25. This is a standard approach to do the grid by doing the grid sensitivity study. Yeah, it's very difficult for the spatial domain to say, foresee and project how it might happen. Time domain possible. Spatial domain is much more complicated to project. Okay, one thing is I wanted to kind of finish it over here is that initial condition is very important for all of us to consider there. At t equal to 0, I have all the variables in the bed. What should be their value? What is the concentration of each of the species there? So if I have a bed like this, question is I said the dci dt equal to whatever, dt dt equal to whatever, and all of those things. So I have to find out these for each of the location, right? Each locations I have to say what are the initial value of all time derivative values should be provided. This is the case with a dynamic simulation, is the initial state there. So what is the initial state? It is okay for many systems to consider the initial state to be steady state condition. This type of variables are denoted in Aspen custom modeler as rate initial. If you declare a time derivative as a rate initial, Aspen will try to solve for a steady state. Can we apply this for adsorption system? No, because it has no steady state, right? So there is no way we can actually apply such kind of a scheme. This is really the trickiest thing for adsorption. We do not know what is the initial state. So you have to go for some simplicity, and that will be future discussion we'll have. So you can say, okay, I can consider the initial state to be when it is fully dissolved. So there is no loading there, and the concentrations everywhere is actually at the inlet concentrations and so on. That's the best guess you can do, right? And that's okay. And I will talk more tomorrow about for adsorption systems. But if you are doing a PFR, if you are doing an CSTR, which has a steady state, this rate initial is a wonderful option. Do not confuse initial condition with initial guess. Initial guess is needed only for algebraic variables. This is with respect to the Newton solver, because remember we always discuss that Newton solver need an initial guess, right? Newton type of solver, because that is where I'm starting. Those are only needed for algebraic variables. So Aspen, when you have give the numbers, it knows what type it is. So whatever is the differential variables, for those it will take those as initial value. Whatever is the algebraic variables, it will consider those as the initial guess for that one. So we'll talk about that more. One thing I like to say and finish it over here is that we generally prefer a step-by-step initialization procedure. The idea is that if I am solving a plug flow reactor and non-isothermal model, I can first solve a model which has got no reaction and it is isothermal, right? It's an easy solution. Then use that solution as the initial guess for when the reaction is turned on. When you use the turn on the reactions, this will be, we can use a homotopy based methods. So remember, you have done probably homotopy based continuation, and you have a continuation parameter there, and then you can slowly crank on the reactions there, and then you have solved everything, but it's still isothermal. Then you turn it to non-isothermal, and then you solve for it. So this writing this initialization routine is actually important for some of the trickiest model. Many of you who have actually used Aspen Plus, and you think actually you drag and drop a box there and block there and click and it runs button, and it works. Why? Because Aspen has done all of these things. They normalize all their things at the boundary. They have an internal solution routine that they have done it. But if you are writing your own code, you have to write this initialization routine for yourself, because you have to, there is no way you can get a good initial guess. So this is the way to trick slowly going there, okay? And the trick is that this is really the takeaway message. You can think about what would be a simpler model that can create a good initial guess for the next round of complicated model. Can I separate my model, look at your equations and say, is it okay for me, I can create a good initial guess for these conditions, but temperature, I have no clue how it will be. And because they are coupled, I cannot solve them together, but I can do an isothermal model and then non-isothermal model, and slowly I can actually create good initial guess. So this is something as an user actually you can come up with it. Once you do it, this initialization routine, and I'll show you where Aspen actually gives you the opportunity, it will actually run it behind the scene for you. That is how all the Aspen Plus routines always runs, behind the scene. We just don't see that, okay? So concluding remarks, I will say that we generally use method of lines, and we use one of the implicit numerical integration approach. We have to keep in mind the accuracy versus computational expense. I will always suggest use an adaptive multi-step method. Now you understand what is adaptive multi-step method means. Then other thing which I did not mention here is anybody who is interested in optimization, because this is a dynamic optimization problem, the preferred approach is orthogonal collocation on finite elements. So something called an OCFE, even any of you have been exposed there. Professor Sachin Patwardhan from IIT Mumbai has got a nice NPTEL video that I also refer my students to. Very nice actually, excellent explanations and show step by step. If you want to learn it from there. Aspen does not have an OCFE implementation, but if you use Python, it has an Pymo has got an OCFE implementations with many of the collocation based methods that you could actually use. For adsorption, we generally use the Redau based collocation methods. It generally works fine. This will be for dynamic optimization. This converts the whole thing into algebraic model, and then it will actually optimize the whole thing. Okay, but I will not spend much time onto this one. We need to carefully decide the initial conditions for the differential variables, and the takeaway message is do not get confused this with the initial guess. They are completely different thing. Okay, I think lunch is ready, everybody is hungry, and what I will do is I will come back and then take the questions, if that makes sense to you all. Okay, very good, thanks.